Welcome back. Today, we're diving deep into a really interesting technical paper. It details Mamba 3.
Right, a new architecture.
Exactly, a new architecture trying to, well, sort of rewrite the rules for large language models. And what's fascinating is the approach. The authors explicitly adopted an inference-first perspective.
And that's key. It's a shift away from just chasing benchmark scores, focusing instead on practical deployment.
It tackles those core pain points, the bottlenecks that, haunt pretty much every large model deployment.
Oh, absolutely. Those pain points are severe, especially at scale. I mean, look at transformers, the standard right now. They're great, but they have these two fundamental weaknesses, both tied to self-attention. First, compute time scales quadratically.
Which just gets brutal fast.
Exactly. And second, the memory needed for that key value cache, KV cache, just grows linearly with the sequence length.
So every new word, every new token makes it more expensive, more memory hungry.
Right. It makes high-speed, large-scale use incredibly difficult, economically speaking. It's often just not feasible.
It's that constant battle, isn't it? Quality versus cost. You want the best model, the smartest outputs, but you can't afford a data center for every user request.
Precisely.
So our mission today is to really unpack how Mamba 3 claims to break that trade-off, how it aims for, well, efficiency and capability together.
And it's important to remember what came before. Mamba 2 and other subquadratic models, they did achieve linear scaling for inference. And that crucial constant memory footprint, that was a big step.
But there were trade-offs.
Big ones. Quality often took a hit. And they really struggled with certain core capabilities, things like state tracking for algorithmic tasks. Plus, and this is critical, they weren't very hardware efficient. Low arithmetic intensity meant the chips were often just waiting around.
So Mama 2 fixed the memory explosion, which was huge, but it wasn't smart enough for some tasks, and it didn't run that fast on the actual hardware. Kind of a mixed bag.
You could say that. Mamba 3 is basically saying, okay, we can keep the good parts, the linear scaling, the constant memory, and fix the weaknesses.
Just more parameters.
No, and that's the elegant part. They're building a more robust, more useful model by incorporating some pretty sophisticated academic principles, drawing heavily from classical state space model theory, or SSMs.
Right, not just brute force. Okay, so let's get into it. They talk about three core innovations. Let's start with the first one, aimed squarely at improving quality. Something about discretization.
Exactly. Trapezoidal discretization. It's about how you translate the continuous math of SSMs into something a computer can actually run.
Okay, break that down. SSMs start as continuous systems, like physics equations.
Kind of, yeah. They describe dynamics evolving smoothly over time. But computers work in steps, discrete moments. So you need a rule, a method, to convert the continuous flow into discrete updates. That's discretization.
Then Mamba 2 used Euler's rule. Sounds simple.
It is simple, maybe too simple.
Yeah.
Euler's rule is what we call a first-order approximation. Imagine you're estimating how far a car travels. Euler's rule is like looking at the speedometer right now and assuming the car holds that exact speed until your next check.
Okay, so it's a bit rough. Doesn't account for acceleration or deceleration between checks.
Precisely. And over a long sequence, those little errors at each step add up. They compound. The math term is O, delta T error. The total error grows linearly with the size of your time step. It limits the model's precision, especially over longer contexts.
So built-in sloppiness, basically. What did Mamba 3 do differently? They couldn't just make the steps infinitely small. That would kill efficiency.
Right. They upgraded their math. They adopted generalized trapezoidal discretization. This is a second-order accurate method.
Second order. So better than Euler's.
Much better. Instead of just looking at the speed now, it's more like considering the speed at the start of the interval and the speed at the end and using an average. It's more informed estimate.
Okay. The paper mentions a data-dependent convex combination of both interval endpoints. That's the averaging idea, looking at both sides.
That's exactly it. And that seemingly small change, looking at both ends, makes a huge difference in overall accuracy. The error drops significantly from O tilde t to a delta tt. It scales with the square of the step size, meaning it gets smaller much faster as steps get smaller.
So less error baked in, which should mean better quality outputs.
Directly. But here's where it gets really interesting, practically speaking. This better math wasn't just about accuracy. It actually allowed them to simplify the model structure.
How so?
They found that this improved discretization, plus some small adjustments, biases on the input-output projections, was powerful enough to replace something else entirely, the short causal convolution layer that previous models needed.
Right, they removed a whole layer just by using better math.
Effectively, yes.
Yeah.
That convolution was there to handle immediate short-range dependencies in language. Mama 3 achieves that same local awareness through the precision of its core recurrence calculation. It's a really neat example of theoretical rigor leading to a cleaner design.
Okay, so better quality through better math and even a simpler structure. That's innovation one. But what about the capability issue? Mamba 2 couldn't do basic logic, right? Parity checking, simple arithmetic.
Yeah, that was a major limitation. Things that require tracking state over time, especially periodic or rotational state. And the root cause was a simplification made in earlier SSMs.
Which was?
They restricted the state transition matrix, the part that governs how the hidden state evolves, to only have real eigenvalues.
Eigenvalues. Okay, refresh my memory on why that matters.
In control theory, real eigenvalues only allow for states that grow, shrink, or stay constant exponentially. They can't represent rotation or oscillation. Think of
Yeah.
it like trying to describe a spinning top using only forward and backward motion. You're missing a fundamental dimension.
So Mamba 2 couldn't spin its hidden state, mathematically speaking. It couldn't track things that cycle, like alternating bits in parity or positions in a sequence.
Exactly right. It lacks the mathematical machinery. So Mamba 3 went back and reintroduced complex valued state spaces.
Complex numbers, like with imaginary parts.
Yes, by allowing the underlying SSM to be complex valued, the state transition can now represent rotation. This gives the model the necessary dynamics to handle those state tracking tasks.
That sounds, well, complex. Does it make the implementation much harder?
You'd think so, but here's the beautiful theoretical connection they uncovered. This complex valued update rule turns out to be mathematically equivalent to doing something else entirely,
Which is?
applying a data-dependent rotary embedding, or ROPE, to the input and output projection matrices.
Rope E. Hold on. Isn't that the positional encoding technique that's super important in transformers? Like in Llama and other big models?
The very same. ROPE uses complex numbers implicitly to rotate embeddings based on position, giving transformers their sense of sequence order.
So Mamba 3 found a way to get that same rope E-like rotational capability, that positional awareness, inside a linear SSM structure, just by embracing complex math.
That's the insight. They basically derived the SSM equivalent of ROPE. It's not bolted on, it emerges naturally from using complex state dynamics. And the results are dramatic.
Dramatic.
Remember Mamba 2 on the parity task? It scored 0.90% accuracy, basically random chance, of Mamba 3 with this complex math leading to the ROPE-like calculation. 100% accuracy on parity. And it gets 98.51% on modular arithmetic. It completely recovers that algorithmic capability.
Wow. Okay, so it wasn't that linear models are fundamentally incapable. It was just that the earlier math was too restricted. They needed the complex numbers.
Precisely. A more complete mathematical formulation unlocked the capability.
Okay, so we have better quality via trapezoidal discretization and recovered capability via complex numbers and this ρ-p equivalence. What's the third innovation? You mentioned hardware efficiency earlier.
Right. This tackles the fast algorithm slow on hardware problem. Even though Mamba 2 was linear time, the actual decoding step generating one token after another was often memory bound.
Explain that again. Why would a linear algorithm be memory bound?
It comes down to arithmetic intensity. That's the ratio of math operations, FLOPS, to the amount of data moved from memory. If that ratio is low, your powerful GPU spends most of its time waiting for data, not actually computing.
So the chip is starved.
Pretty much. A standard SSM, which processes things one input and one output at a time, SISO, single input, single output, has a constant and typically low arithmetic intensity. It just doesn't give the chip enough work to do relative to the memory fetches.
Like feeding a race car engine with an eyedropper.
That's a great analogy. So Mamba 3 introduces a structural change,
Mhm.
a multi-input, multi-output system, or MIMO.
Okay, MIMO. How does that help?
Instead of the core state update being based on simpler vector operations, like an outer product in SISO, it shifts to being based on matrix multiplications.
Matrix multiplications.
Yeah.
Those are things GPUs are really good at, right?
Exactly. They are compute-dense operations. By introducing an extra dimension, or rank, let's call it $2, into these matrices, the arithmetic intensity now scales with $3. It's not constant anymore.
So by making the internal calculations involve bigger matrices, you increase the compute-to-memory ratio. You give the GPU more to chew on for each memory access.
Precisely. The MIMO structure allows the model to feed the accelerator bigger chunks of work derived from the state. This pushes the decoding process away from being memory-bound and towards being compute-bound, which means the hardware is actually utilized much more effectively.
And crucially, they did this without sacrificing the linear scaling or constant memory.
That's the beauty of it. The state size itself remains constant. They're not increasing the memory footprint exponentially. They're just using the existing fixed memory state more efficiently to generate more computation.
It's pure hardware-aware optimization.
Yes, and it pays off. The paper shows the MIMO variant gives a noticeable boost, like a 1.2-point gain in average accuracy over the CISO Mamba 3 at the 440M scale, just from better hardware utilization. It validates that whole inference-first idea.
Okay, so 3 big academic-inspired improvements: better discretization for quality, complex numbers for capability, and MIMO for hardware efficiency. How does it all stack up overall?
Looking at the big picture, across standard language benchmarks, HelloSwag, PIQA, ArcChallenge Mamba 3 performs really well.
Better than transformers.
At the tested scales, from around 180 million parameters up to 1.5 billion, Mamba 3 consistently matches or slightly outperforms the transformer baselines, and it's clearly better than Mamba 2 and other non-transformer models they compared against.
And they also pulled in some standard tricks from modern transformers, right? Like normalizations.
Yeah, they incorporated things like pre-normalization and QK normalization. Similar to what you see in models like Llama, it shows they're integrating best practices from everywhere, not just SSM theory.
Sure.
But the really telling graphic in the paper is the Pareto frontier plot.
Ah, the efficiency trade-off curve. Performance versus cost.
Exactly. They plot model performance perplexity, where lower is better against a proxy for inference speed, which is related to the state size. And Mamba 3, especially the MIMO variant, clearly pushes that frontier outwards.
Meaning for the same amount of compute cost or state size, you get better performance. Or conversely, for a desired performance level, Mamba 3 is faster or cheaper.
That's it precisely. They've fundamentally shifted the curve. You get more bang for your buck, which is the whole point of optimizing for inference.
Okay, it sounds incredibly promising, but no model is perfect. What's the catch? Where does it still lag?
The main known limitation, which is sort of inherent to fixed-state models, is retrieval.
Retrieval, like recalling specific facts from a long context.
Exactly. Because Mamba 3 has to compress all information from the past into its fixed-size state vector, it struggles compared to attention models when you need to pull out a very specific detail from way back in a long, unstructured document. Attention can directly look back. Mamba has to rely on its compressed memory.
So it might be better at summarizing or understanding the gist, but worse at finding that one specific name or number mentioned 50 pages ago.
Generally, yes. The paper notes Mamba 3 is better at out-of-distribution retrieval than Mamba 2, which is progress, but it still doesn't match attention-based models on complex, long-context retrieval tasks. That fixed-state compression has its limits.
Right, that trade-off is still there, even if it's been improved. So wrapping this up, what's the big takeaway for you listening to this? Mamba 3 feels like a really successful blend of deep academic ideas and smart practical engineering.
I think so.
It's focused squarely on making models useful and efficient in practice, hitting that inference speed goal, while simultaneously using advanced math to recover fundamental capabilities like state tracking that were lost before.
Yeah, the core insight and why this work is significant is that progress isn't just about scaling up parameters anymore. It's about weaving sophisticated concepts, better numerical methods, complex algebra, understanding the hardware right into the architecture itself.
Smarter, not just bigger.
Exactly. It suggests the future of efficient AI might rely as much on clever applied mathematics as it does on raw compute power.
Okay, that leaves us with a final thought, something for you to ponder. Given that this retrieval gap is still the main challenge for these fixed-state models, how long before we see hybrids? Could we see a Mamba 3 core retaining that linear efficiency, but maybe with a small targeted attention mechanism bolted on just for specific retrieval needs? Could that bridge the final gap with transformers?
It's an interesting possibility, combining the best of both worlds.
Something to think about. We'll leave it there for this deep dive.
All right, let's dive into this really fascinating paper on Mamba 3. It's a new AI architecture that's making some serious waves, and it's aiming to completely reshape how we think about building these big sequence models. You know, for years, AI developers have been stuck with a really tough choice. It's felt like you have to pick your poison. You can have a model that's powerful, or one that's super clever, or one that's just lightning fast. But getting all three at once, that has been the holy grail, a problem we can really think of as the AI trilemma. So here are the 3 points of that trilemma: quality, capability, and efficiency. And here's the catch. Traditionally, you could pick two. You could have a high-quality model that was really capable, but it was probably slow and expensive. Or you could have a fast, efficient model that just wasn't that smart. Getting all three has been the grand challenge, especially for the transformer models that have dominated the field. So in this explainer, here's what we're going to do. We're going to break down exactly how the Mamba 3 paper claims to have solved this trilemma. We'll start with the problem itself. Then we'll dive into the 3 big innovations they introduced, and finally, we'll look at the results to see if it all actually works.
All right, so first up, let's really dig into the problem Mamba 3 was built to solve. What were the limitations they were trying to overcome?
Well, you've basically got two camps. On one side, you have transformers, the undisputed champs, incredibly powerful. But their big weakness, as you can see, is that they get really slow and expensive as sequences get longer. On the other side, you have these promising alternatives called state space models, or SSMs. They promise to be way more efficient, but the reality was that earlier versions just couldn't compete on quality and raw capability. It was a classic trade-off.
Okay, innovation number 1. This is a big one, and it gets right to the heart of the quality part of the trilemma. It's all about finding a fundamentally better way for the model to process information.
And it all starts with a concept from classical mathematics called discretization. So imagine you have a smooth, continuous sound wave. A computer can't see that continuous wave. It needs to break it down into a series of distinct digital steps. That process of turning the smooth, continuous reality into discrete steps a computer can understand, that's discretization.
And this slide just shows the difference perfectly. Look at the left. That's the old way. It's kind of like drawing a curve using clunky, blocky steps. It gets the general idea, but you lose a lot of the detail. Now, look at the right. That's the Mamba 3 way. It uses a much more sophisticated method that hugs the curve, capturing way more information accurately. It's a small change on paper, but it has a huge impact.
So the bottom line here is that this very clever choice, something rooted in classical math, directly translates into a much more expressive and higher quality model. It's a beautiful example of first principles leading to better performance. All right, that was quality. Now let's talk about capability. This is innovation number 2, and it's all about giving the model new reasoning skills that previous linear models just didn't have. Now, you'd think this would be easy, right? It's just simple addition and subtraction. But a task like this, which is really about keeping track of an alternating state, was a massive problem for a lot of earlier SSMs. To solve it, a model needs a kind of memory that can rotate or cycle through different states. And here's why they struggled. As this slide points out, the problem was that these older models were basically stuck thinking with real numbers. And real numbers are great for things that go up or down in a straight line, but they're terrible at representing things that go in circles or oscillate, which is exactly what's needed here.
So how does Mamba 3 fix this? Well, it's a really elegant trick. It stops thinking only in real numbers and starts using complex numbers for its internal state. This immediately allows it to represent those crucial rotational dynamics. And even better, they found a super efficient way to implement it. It's a fantastic example of using a richer mathematical space to unlock brand new abilities.
And that brings us to the third and final piece of our trilemma, efficiency. Because let's be real, a model can be the smartest thing in the world, but if it's too slow and expensive to actually run, who's going to use it? This is all about raw speed.
This all comes down to a really important hardware concept called arithmetic intensity. You want your expensive GPUs doing what they do best, crunching numbers. You don't want them sitting around, twiddling their thumbs, waiting for data to arrive from memory. High arithmetic intensity means the chip is always busy doing useful work.
To crank up that intensity, Mamba 3 makes a really key architectural shift. Older models were what we call CISO, single input, single output. Think of it like a one-lane road. Data gets processed one piece at a time. Mamba 3 switches to a MIMO design, multi-input, multi-output. This is like turning that road into a multi-lane superhighway, and it fundamentally changes the math in a way that modern GPUs absolutely love. A huge jump in arithmetic intensity. Now, you can see the math here, but what it really means is that the hardware is just way busier doing useful computations. It's squeezing every last drop of performance out of the silicon. Okay, so we've seen the 3 big ideas: a better recurrence for quality, complex states for new capabilities, and a new design for efficiency. But does it all add up? Let's look at the results and see if Mamba 3 actually delivers on the promise.
And wow, just look at this. Remember that simple counting task we talked about? Mamba 2 completely fails, less than 1% accuracy. Mamba 3 gets a perfect score, 100%. That's not just an improvement, that's unlocking a capability that was basically impossible before.
And it's not just on these tricky little puzzles. When you look at standard language modeling benchmarks, the story is the same. Mamba 3 comes out on top again, beating both a comparable transformer and its own predecessor, Mamba 2.
But for me, this graph tells the whole story. This curve is what's known as a Pareto frontier. It represents the best possible trade-off you can get between performance and cost. And what Mamba 3 does is it pushes that entire frontier forward. It's literally redefining what the best possible trade-off is. So the takeaway here is crystal clear. Mamba 3 isn't just a little bit better here or a little bit faster there. It's giving you more performance for the same or even less cost. It really is the full package: quality, capability, and efficiency. It solves the trilemma.
And the authors themselves put it best in the paper, saying their new architecture sets a new standard for performance within a fixed budget. It's a bold claim, but the data seems to back it up.
You know, what's so exciting about a paper like this isn't just the model itself. It's what it represents. It shows us that these trade-offs we thought were just fundamental laws of AI, maybe they aren't. It proves that by going back to first principles, we can break through old limitations. And that leaves us with a really thrilling question. If we can solve this problem, what other impossible problems are next?